Okay, good morning and welcome everybody to this second day of the QTML workshop. And this morning's session will start with Lectio magistralis. And the idea behind this Lectio magistralis is that, okay, this workshop witnesses the presence of participants with an heterogeneous background. And so probably each one has just a partial view of the field of quantum machine learning. And then it would be nice to have a talk that gives us a global perspective on this field. Also, being this computer science department, there could be some people behind our workshop that is interesting to see what is boiling in at the interface between quantum mechanics and machine learning. And so for them, it would be nice to have an elementary introduction to this field. Last but not least, we would also pay tribute to a person that has given seminal and very fundamental contribution to this field. So for all these reasons, I am very glad to leave the floor to Professor Seth Lloyd from MIT, who will talk about prospects for quantum machine learning.
Thank you very much. And is there a laser pointer? Laser pointer? Okay. Great. So let's see. So how many people here are from the workshop? How many people are just coming in to see what's going on? Only a few people. Okay, good. Well, first of all, before talking about quantum machine learning, or as you can see, I'm going to talk about a particular aspect of quantum machine learning I call universal deep quantum learning. And I thought I'd talk about this because it sounds cool. But I'd like to thank the organizers, Alessandro Di Pietro and Stefano Mancini, for bringing us all here. This is the first time I've spent any time in Verona. It is a very beautiful city. Of course, I've read about it many times. It is the city of Catullus, the city where Stilicho defeated Alaric, the city where Dante spent some of the happiest years of his life with Can Grande. And of course, let us not forget, as I discovered last night in the cantina of the Osteria Ugo, it is the city where Giulietta e Romeo I facea mattina, according to legend. This is, I won't translate this. For people who know what it means, that's fine. But other people, I can't translate this. It is a very beautiful city, and I've been wandering all around it, seeing wonderful art from Mantegna, Pisanello. It is a fantastic place, and thank you very much for inviting me and all of us here to your beautiful city. Okay, so I'd like to tell you about, as I say, about universal deep quantum learning. And as part of this, I'm going to give an introduction to the entire field of quantum machine learning. Actually, I won't be talking about all aspects of quantum machine learning, because machine learning, of course, is a very big field, classical machine learning. And it's developed many extremely powerful techniques for using classical computers to analyze big data, large amounts of data. I mean, this is not, everybody knows this. It's become very trendy recently. For the people here from machine learning, as you know, it was not always very trendy. I remember when I was a postdoc at Caltech in the late 1980s, I would go and visit John Hopfield. And this was a time where, if you have been in the field for that long, you remember they had, rudimentary neural networks with, a few dozens or tens or hundreds of artificial neurons. And they could recognize some patterns and memorize a few patterns, but then that was basically it. And it wasn't doing that much. And I remember Hopfield saying at the time, you know, I understand that things aren't working as well as they might, but I believe that if we had computers that were 1,000,000 times more powerful, and if we had 1,000,000,000 times the amount of data, that this would work, I swear. And actually, that's basically what's happened. Many, if not most of the techniques of classical machine learning were developed in the, I mean, of course, classical machine learning, the idea of artificial neural nets has been around since the 1950s with the perceptron. But many of the ideas that we look at right now, like ideas of deep learning, contrastive divergence, Hopfield nets, et cetera, date back to the 1980s and 90s. It is a very beautiful field mathematically and very inspiring. And it's only recently, in the last few years, really, I would say in the last 5 years or so, that machine learning, classical machine learning, has really started to live up to its promise. I remember as a professor at MIT, of course, as an Institute of Technology, they are early adopters of all kinds of technologies. So who here has been to MIT? Okay, so if you come into MIT by the main entrance on Massachusetts Avenue, there's an automatic door. And the automatic door is apparently the oldest continually operating automatic door in the world. But of course, you know, they said, if we're an Institute of Technology, we need an automatic door. So it's been there since 1912 or something like that, or 1914. And of course, it's always broken. Similarly with machine learning, again, in the late 1990s, around 2000 or so, MIT, some very clever professor of electrical engineering and computer science at MIT convinced the institute to fire its telephone operators and to replace it with a voice-operated system activated by machine learning. And for the next probably 5 or 6 years, your experience in calling MIT is you call up, you'd say, I'd like to speak with Professor Jane Smith. And the computerized voice would say, now ringing Mary Lefkowitz. If this is not the right number, press 9. Boop. Jane Smith. Now ringing Hua Zhong. Beep, 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 beep. It went on for years. And now, of course, you know, voice recognition software is everywhere, and it's very good. Your smartphone is very good at recognizing your own voice, and one of the main reasons of this is that it's applied powerful methods of machine learning, including deep learning, that I'm going to talk about today, to the problem of recognizing patterns in data. So let me go and let's look a little bit at what is deep learning, what kind of patterns can be learned by classical computers or by quantum computer. And now I'll raise the central question. Are there patterns in data that can be learned by a quantum computer but not by a classical computer? Now, I should say that in this talk, and by the way, the answer to this question is we don't really know. I'll give some evidence that this is the case, but in general, we don't know if this is so. Now, I'm actually, for this talk, I'm really going to look at the application of quantum computers to machine learning. Of course, you can apply classical machine learning techniques to quantum mechanical systems, and we've heard some nice talks about this, to learn patterns in quantum data, to try to tune your quantum devices, to test the effects of different kinds of models. So I'm not really going to talk about classical computers applied to quantum systems. And I already talked about classical computers applied to classical data. So here I'm going to talk primarily about quantum computers applied to classical data. That is, can quantum computers recognize patterns in classical data that couldn't be recognized classically? And I'll also talk briefly about quantum computers applied to quantum data. This is a field where, what do I mean by quantum data? Quantum data are the sets of quantum states produced by a quantum computer. They're the, by quantum apparatus. And as we'll see, there are many nice methods for taking the quantum states, say for instance states of light that are produced by some nonlinear quantum optical system, putting them into a quantum information processor, which could be a very small quantum information processor, and then processing these quantum states to reveal features of the system that you couldn't reveal classically. I would say that that's probably, in the short term, the strongest application of quantum machine learning. However, because we live in an age where we're just at a very exciting time for quantum computers, where for the very first time, we have, or about to have, quantum computers which have, you know, Google claims they're going to have a quantum computer with 49 qubits this year. IBM has a quantum computer with 18 qubits right now. We're just at the stage with, even though this is a very small number of quantum bits, that we can reasonably expect quantum computers to explore phenomena and generate and recognize patterns that we couldn't recognize classically. Because to simulate a 49 qubit quantum computer on a classical computer is beyond the reach of by far the most powerful classical computers and will remain so for decades, if not forever. Okay, so what is deep learning? We actually heard a bunch of things about this, but, oh, sorry, excuse me. This is a review of quantum computing. Well, what is deep learning? So actually, my background in quantum information dates back a long way. I became interested in quantum mechanics and information processing when I was doing a master's degree in history and philosophy of science at Cambridge University. Ironically, all the stuff that I do now is based on my one graduate degree in humanities. Showing the humanities can't be all that bad. About 5 years ago, my postdoc, Patrick Rebenstrost, who's from Munich, came into my office and said, Seth, we should look at quantum machine learning. And I said, great, what's machine learning? I kind of knew, but I didn't really know very much. And Patrick started to explain some of the basic techniques of machine learning, and I realized quite rapidly that we could quantize these and make quantum algorithms which could do better than classical algorithms. And after we'd worked on a few of these, and I'll describe these, some of these quantum algorithms on the next page of my PowerPoint presentation, then Patrick said, well, let's look at deep learning. I said, deep learning, that sounds amazing. I got very excited about the idea of deep learning. It said, deep learning, so computers are going to tell us about deep things like, you know, life and truth and happiness and love. You know, what better place than here to talk about love. But Patrick quickly pointed out that it's not about that. It's just, you know, looking at neural networks with many layers, so they're deep. Damn. Who knows? Maybe classical computers will teach us about love. Some of my students at MIT seem to be more in love with their computers than with humanity as a whole. But I'm not sure about that. Actually, by the way, this is a, if we have time, we can talk about at the end about whether current deep learning, classical deep learning algorithms, it's very exciting what they're doing, you know, beating the world champion of Go at Go, which is a remarkable achievement, recognizing things that people say, which is also a remarkable achievement. But I must say that I myself am very unconvinced that the current path of deep classical learning will give us computers that actually understand and are able to deal with the same kinds of aspects of life that human beings can, for a variety of reasons. Okay. So let's look at these. First, I'd like to give a little review of problems that quantum computers can solve, where we do know that, at least in principle, quantum computers, including rather small quantum computers of the sort that we're going to have in the next few years, can actually make a very serious, do some serious damage when it comes to learning patterns. So let's look at some quantum machine learning algorithms. I'm going to talk now about a large class of quantum machine learning algorithms that are based on the abilities of quantum computers to do linear algebra. So The basic picture right here is that, classical machine learning, we have data, which are typically expressed to us in terms of vectors in a very high-dimensional vector space. And I'm going to look at vectors over the complex numbers. Why? Because quantum computation and quantum mechanics is all about vectors over complex numbers. The basic formulation of quantum mechanics is expressed in terms of vectors over complex numbers. By the way, who here has a background in quantum mechanics? Who here doesn't have a background in quantum mechanics? Okay. Who here both does and doesn't have a background in quantum mechanics? Okay. The true quantum people. So if you don't have a background in quantum mechanics, I think perhaps the most important feature to know is that the basic structure of quantum mechanics, the states of quantum mechanical systems, like for instance, the configuration of electrons in an atom, or the state of an elementary particle, or the state of a superconducting quantum circuit, they're represented by vectors in very high-dimensional vector spaces. And indeed, for this form of algorithm I'm describing, the primary feature that one must do is to take these vectors, these classical vectors, and map them into quantum vectors. And if you don't have a background in quantum mechanics, all that this funny bracket called a Dirac bracket means is that this is a vector in a high-dimensional vector space. It sits in c to the n for some power of n. Now, if one can do this, then one can actually do something quite remarkable. And the reason is the following. If I have a vector, a classical vector that sits in a very high-dimensional vector space, let's say little n here is very high-dimensional, the quantum mechanical vector that corresponds to that sits in a much lower number of bits. So for instance, to store this classical data in memory, let's suppose n is 10 to the 12th, just for the heck of it. So we have 10 to the 12th, order of 10 to the 12th bits. We need actually 10 to the 12th actual physical bits in this memory to store this information. But the corresponding quantum mechanical vector is a vector over log to the base 2 of 10 to the 12th bits. And since 2 to the 10th is 10 to the 3, very important feature of, in fact, of life, then 10 to the 12th is 2 to the 40th. So a vector, a classical vector of 10 to the 12th bits corresponds to a quantum mechanical vector over only 40 quantum mechanical bits, 40 qubits. That is, there's a tremendous compression of the representation of this information when one maps it into a quantum mechanical system. And I would say the central open question of how you actually, whether quantum computers can, in these kind of small quantum computers that are being constructed right now, can really actually find patterns in data that we couldn't find classically, is whether it's possible to do this in an efficient way. Now, to do this with a quantum device, you need what's called a quantum random access memory. And for the purposes of this talk, a quantum random access memory is just something that takes a very large classical vector of data and maps it into a quantum state. Now, I've forgotten once again to bring a prop for doing this, so I'm going to have to ask you to use your imagination. So actually, now this actually is not an easy thing to do, but mapping classical data into quantum state is easy. So imagine, I don't have it right here, I usually carry around with me a DVD. It's actually the one I carry around is one that somebody sent me a number of years ago called Is the Bible True? So imagine I'm carrying this I actually have not looked at it, but it's very useful for lectures like this, so I'm sorry I didn't bring it. Imagine have a DVD, and I have this DVD. The DVD is a set of around 10 to the 10th little mirrors. The size of the mirrors is a few times the wavelength of light. There are a few microns on each side. And and the idea is that the presence of a mirror signifies a 1, and the absence of a mirror signifies a 0. So the way you ordinarily read a DVD is it spins around, and you shine a laser, diffraction-limited laser off the DVD, and if the light reflects off, then you have a 1, and if it doesn't reflect off, you have a 0. And so you can sequentially read out this DVD, the information on this DVD. However, you can also actually encode this information in a quantum state. Suppose I take a laser, oops, sorry, and I generate a single, photon. Here's a lot of photons. But I generate a single photon. I take a lens, a concave lens. I expand the spatial mode of the single photon, so this one photon bounces off the entire DVD. Then what you find is in the places where there are mirrors, the photon has a small amplitude of being in the spatial mode that corresponds to this mirror. And in the places where there are not mirrors, the photon is absorbed, and so it doesn't come out. So the state of the single photon after it's bounced off the DVD is a quantum mechanical superposition of being in all the spatial modes corresponding to mirrors. So it's a quantum state of a single photon, and it encodes the information on the entire DVD. This is not that hard to do, but of course the problem is it's not expressed in terms of quantum bits. So what would be a great technological advance would be to build a quantum random access memory that would allow you to encode information into quantum bits. Now we have designs for this, and in fact, Fabio Sciarrino at University of Roma La Sapienza has done proof of principle experiments to show that this is possible. But to do this on a large scale, you actually have to have a quantum apparatus that addresses many classical degrees of freedom where the information is stored. So you need to build a rather large quantum device. I'm tempted to tell a story about this. Maybe I will. Well, actually, I'll tell a story. Let me just go over this and then let me tell this story about the design that we have for this, for quantum random access memory, comes with Vittorio Giovinetti and Lorenzo Maccone, my longtime collaborators here in Italy. And I will tell you how it came about in just a second. Okay, but suppose you have this quantum random access memory. You take your classical data, you encode it as a quantum mechanical state. You have n components to this data, log n qubits in this quantum mechanical state. So 10 to the 12th bits have now been encoded in 40 quantum bits. Now you can do all kinds of operations on a quantum computer that you couldn't do classically. Because quantum computers, rather as is pretty well known these days, because the fundamental physics of quantum mechanics is based on linear algebra, on the manipulation of vectors in high-dimensional vector spaces, quantum computers can do all kinds of operations in linear algebra exponentially faster than classical computers. So for instance, suppose you wish to take a discrete Fourier transform of this data. The quantum Fourier transform will perform essentially exactly the same operation as a discrete Fourier transform on this vector, but it will do it in time that's exponentially faster. The discrete Fourier transform classically takes time n log n. The quantum Fourier transform takes time log n quantity squared. So exponentially faster than the classical data. And for instance, you can check to see if two states, the Fourier transform of this vector has a high overlap with another vector. And this is a problem that takes time order n log n. On a classical computer, it takes time order log n squared on a quantum computer, exponentially faster. Again, you can use quantum computers. One well-known algorithm tells you how you can invert matrices. So you can invert n by n matrices that are sparse or low rank. You can construct the pseudo-inverse of a low-rank matrix. You can construct these in time where for a classical computer, this matrix inversion for a sparse matrix takes time n log n. Then for a quantum computer, again, it takes time order log n squared. And this means you can solve all kinds of problems. For example, you can do linear and polynomial regressions to fit data. You can take a bunch of data points, and you can construct the least squares fit for these data points. Or again, using this matrix inversion algorithm, you can construct support vector machines. If you have two sets of data, one cloud over here, another cloud of data over here, and you're given the guarantee that they're well separated, then your goal is to construct the optimal separating hyperplane or hypersurface between them. And again, once again, this is just a question of linear algebra and solving a large number of equations, order n equations on a high-dimensional space. Once again, this takes time, order log n squared on a quantum computer, takes time order n squared on a classical computer. You can perform principal component analysis. So that is to say you want to find the eigenvectors of the following object. This is a matrix. This is the covariance matrix, about which we heard so much yesterday. I don't think I've heard ever so much about covariance matrices in 45 minutes ever, as in the talk yesterday. Some of it went by a little fast for me, but certainly there was a lot of information. It might have been actually done better to have been compressed into a quantum state. So the covariance matrix for some data, if you have a bunch of data points, a large number of vectors, is simply this object, which is the sum over each vector x times the transpose of x, or since I'm a quantum guy, the Hermitian conjugate of x. This represents the pairwise correlations between the components of the data. And you'll see that if I actually map this into a quantum vector, this is just the density matrix for the data. So in principal component analysis extracts eigenvectors and eigenvalues of this density matrix for the data, and it does so again in time log n squared. And this is an example of why quantum computers are even small quantum computers are very good at extracting information about quantum data. Suppose I'm sampling the quantum states that come out of a system. They have some density matrix. And then I can use this principal component analysis algorithm to find out, for instance, if this density matrix is low rank, or if it's a pure state. It's a very interesting question. And once again, you can do this exponentially faster than you could do by conventional classical tomography. You can calculate topological invariance of data. There's a rather elegant and beautiful form of classical data analysis called persistent homology. And the idea is your data is sampled from something out in the classical world, and the thing that it's sampled from is a manifold that has some topology. And you get a discretized picture of this continuous structure. And your goal is to extract the topology, or the homology in this case, which is the holes and voids, etc. The number of holes and voids at a particular dimension is called the Betti number. And the goal of persistent homology is to figure out how many holes and voids there are in this data. Of course, it's a funny thing, right? I mean, this is actually, it took me quite a long time. This is work with Paolo Zanardi, it took us quite a long time to figure out what was going classically. I mean, if I have a discretized picture of some data, here's the data right here. Now, this is data that has a hole in it, right? I've drawn the picture of the hole. But if it's discretized, the question is, how do you find that there's a hole? If I look up really close, then it's all holes. There's nothing but holes in this data. And the idea classically is you kind of like fuzz it out. My eyes are pretty bad. When it's fuzzed from this far away, I say, oh, look, there's a fuzzy blob with a hole in the middle. And then if you look at it from further away, in my case, I say, wow, it's just a fuzzy blob. I can't see any hole or not. And it turns out that by methods of algebraic topology, you can map this data onto a high-dimensional space. And then find holes and voids by doing linear algebra on this space. And this makes it a perfect algorithm for doing quantum computing. You map the data onto very high-dimensional vectors. You have to find the kernel of a very high-dimensional matrix called the simplicial Laplacian. And then once you do that, you can find the holes and voids in this data. And again, you can do this in time exponentially faster than you can classically. And there are many, many possible algorithms. Patrick and I have a very fun algorithm. We've been applying it to ideas of finance. Patrick has a goal. He wants to find the billion-dollar quantum algorithm. And we have a nice algorithm, if I may say so. What it does is, if you're given the covariance matrix, you're given vectors. Your data is in the form of vectors of historical prices for stocks on the stock exchange. Well, the first thing you might want to do with that is do principal component analysis, because if you actually look at this data of prices on the stock exchange, I guarantee you right now, there's a lot of computer power, classical computer power, going to look for principal components of this data on the stock exchange. Why would you do that? So in principal component analysis, if this covariance matrix is very low rank, so there are only a few eigenvectors that have large eigenvalues, then it means that all the stocks in the stock exchange are following some hidden underlying patterns, which are given by these eigenvectors. And if you know what they are, then you can actually bet on things, on the future prices, because you know how they're correlated with each other. So if the covariance matrix is very low rank, it means that the stocks are highly correlated with each other, the motions of stocks. On the other hand, if it's high rank, then it means that they may be correlated, but the correlations are faint and there's not a lot that you can do. In a quantum finance algorithm, what we do is we give an algorithm. So in portfolio management, a common goal is to say, I wish to have a portfolio, a set of stocks, which maximizes return for a particular value of risk. So you maximize your average return for a fixed value of the standard deviation of your return. And this algorithm will actually tell you what the maximum return is that you can get for a fixed risk. And it will also give you, in quantum form, the portfolio that you should invest in. Pretty good. This actually suggests that with time we really should put some effort into constructing these quantum random access memories so that we can actually pop this data into our small quantum computers and get fabulously wealthy. Well, I'll speak for myself, but maybe for a lot of other people in this room. If I had wanted to become fabulously wealthy, I should have chosen another profession.
We all agree we're here for love, right?
Yeah, we're all here for love, right? It's a deep thing, that's right. That's right. And I also don't believe that, machine learning systems are going to replace the kind of things that people in this room do anytime soon either, though they may be very helpful for us. Though, I mean, actually right now, of course, since I started working on this quantum machine learning stuff, now, not only are companies like Google and Intel and Microsoft and IBM and Alibaba and Tencent and Huawei putting tens of millions of dollars into building quantum computers. There are all these little startups that are like popping up like fungi all over the place. So yes, it's clear that it's both an exciting time for quantum computing, and we may be in the midst of a quantum bubble, or the quabble, as I call it. All right. Anyway, so enough about these. There are a lot of these algorithms. Oh, and by the way, there are a bunch more. There's some very nice work from Microsoft on doing linear programming and using quantum computers. Essentially, I mean, once you know pretty much all the basic linear algebra subroutines, which are called the BLAS, the things that go into MATLAB, pretty much all of them, like matrix multiplication, diagonalizing matrices, inverting matrices, doing Fourier transforms, almost all of these can be sped up exponentially on a quantum computer. And so there's a large set of possible data analysis algorithms that one can come up with that quantum computers could in principle help with. All right. Oh, this is an example of this topological analysis. Let me see if I can't actually, oops. Let me see if I can't make this bigger. How do you make things bigger here? Let's see. I'm very bad with PowerPoint kinds of things. Well, I'm sorry. I don't know. Okay, so let me show you. This is a picture. One of my collaborators, and all my collaborators are Italian, as you notice. This is because somebody's got to come to Italy and eat delicious food here. So this is from a paper with one of my collaborators, Francesco Vaccarino. This diagram right here. You can see it's got some kind of topological structure. This is actually an example of applying these classical algorithms for topological analysis to brain data from the brain. And what they do is they take this data and they try to figure out what are the kind of connected components of the brain while people are thinking. So while it's from functional magnetic resonance imaging data, and they looked, this one on the left, they took a bunch of volunteers and they had them in an ordinary resting state, just kind of thinking about ordinary things. And they looked at what was going on in their brain. And they identified that there are a set of about 1, 2, 3, 4, 5, 6, 7 clusters of highly connected neurons here. These, you can see they're in different colors here. These are the connections, means that there's lots of signals going back and forth between these neurons. And you see that there's also each of these, so these represent kind of distinct thought processes that are going on. And there's a lot of evidence, just psychological evidence, not just MRI evidence, that in our resting state, we're thinking of about 7 things simultaneously, in parallel with each other. And these different thought processes are kind of talking with each other. These show that these are different, signals going back and forth between these thought processes. This one on the right, this, by the way, this diagram was Wired Magazine's best scientific diagram from 2015. Why? Because this graph on the right is the same group of volunteers, but after they had taken hallucinogenic mushrooms, psilocybin. It's another fungi issue right here. And well, all I can say is, wow, everything's connected, whoa. You can't deny it. For those of you who've taken hallucinogenic mushrooms, this explains a lot. All right. So now let's look at machine learning in general. So and get on to the topic of deep learning. So I mean, the general, of course we heard reviews about this yesterday. But we heard reviews from people who were very knowledgeable about machine learning, and sometimes it's better to have a review from someone like me who is not. So, I mean, the basic picture is you're given data and you want to find patterns in this data. And there, broadly speaking, there are 2 kinds of machine learning, though we actually heard about several more. In supervised learning, you're giving a training set that associates classifier labels C to each data point D. For example, in pictures of handwriting, here's a data point, it's a handwritten 5, and here is a classifier label that says this is a 5. And so given a lot of this training data where you're told what these different numbers are, your goal is to find an algorithm that assigns a new data point D to the correct class C. So given a new handwritten number, it's supposed to, your data analysis, your machine learning method is supposed to say it's a 5, or it's a 1, or it's a 3. There are many very successful methods of supervised learning out there. Harder, but more interesting, or maybe more interesting but harder, is unsupervised learning, where you're given data D and you want to find the classes C that naturally partition the data. And having found these classes, then you can try to assign new data to particular classes. So a famous recent example of this is folks at Google using a deep neural network were able to analyze vast amounts of data of images from the internet, and they found, that they identified a large class of them, and this class turned out to be pictures of kittens, right? Pictures of kittens, and then, was able to say, take another picture and say, is it a kitten or not? Now, of course, this is a little strange because actually just from a Bayesian perspective, the prior probability that a picture taken from the internet is a kitten is already very high. So merely saying it's a kitten already has a high probability of success. But I gather that Google's algorithm had a higher probability of success than merely guessing that it's a kitten. This is harder because it's not clear how you divide things up into classes. But there's a lot of success in actually doing this, as the kitten example shows. Now, what about deep learning? So, well, in deep learning, you have networks. And here's an example, a physics-based example called a Boltzmann machine. These were proposed by people like Hopfield and Hinton back in the 80s. And you have, just as a picture, you have a bunch of layers. See, there are a lot of layers here. Well, actually, there's not that many, because I've learned that in these kinds of things, you have to draw so many lines. You should never draw too many layers. Let's say that you present, so the idea is you present your data at this visible layer, and the information propagates through these hidden layers, getting processed as it goes. And here are these classifier layers up here. So you could present pictures of handwriting down here. It gets processed as it moves through these hidden layers. And up here it says, it's a 5. Say this is the 5 neuron that says, look, it's a 5, or this says, it's a 3. And the way that a Boltzmann machine works, it's a very physicsy based way of doing machine learning. Not surprising, because Hopfield is a physicist. He was a solid-state physicist. And it's based on what's called an icing model, which is just a set of spins. You have a spin that can be spin up or spin down at each point. This is the energy term that corresponds to spin up or spin down. And you can have interactions with these spins. So this could be, spin I and spin J have a low energy if they're aligned with each other, a ferromagnetic interaction, or they have a low energy if you're anti-aligned with each other, an anti-ferromagnetic interaction. And then you come up with an energy functional, a Hamiltonian, which summarizes the biases that you have for, or weights that you press on satisfying, for instance, this spin likes to be up. There's like a magnetic field that likes to make this spin up. But, if it's convinced by its neighbors to be down, it will be down. This interaction says spin 1 and 2 like to be up together, and spin 1 and 5 like to be opposite. So it's an icing model with tunable weights, these little energy terms right here. And the goal of this method is to encode a computation, or encode the information processing in the low energy states of this Hamiltonian. So these terms embody constraints, and you wish to have look for states that satisfy the largest number of the constraints. And of course, in machine learning, the constraints are, if I put a 5 in here, I wish to set these weights so that this neuron is likely to say, it's a 5. That's the kind of constraint that you're trying to exemplify. Now, there's a very important piece of these networks, and that is that these networks are computationally universal. And I'll just actually sketch a proof of this right here. So it's actually been known since the 1980s that finding the ground state or low energy states of the icing model Hamiltonian of this energy is computationally universal. This is a result from Verona. But I will sketch a much simpler proof of this. It was alluded to yesterday. The idea is that you can encode in these low energy states, you can encode logical relations in these constraints. So for example, suppose that this spin has, by this computation, by other parts of the computation, it's been constrained to be spin up, which we'll call 0, and spin down we call 1. And I want this other spin, this other variable, to be the opposite. Well, if I put an anti-ferromagnetic interaction here, so that if X is spin up, then Y is constrained to be spin down in the low energy state. And that just means that Y is not X from a logical standpoint. A copying operation is even simpler. I want to copy this. So suppose that this variable has been fixed by energetic constraints to be down, let's say 1, and I want these other variables to be 1. Well, I just connect these variables with ferromagnetic constraints so that if this is spin down, these spins like to be down as well. And it's not hard to convince yourself that by tuning the interactions and the individual terms on a little diagram like this, you can set it so in the low energy states, if X and Y have been constrained to take on particular logical values, that this spin right here, Z, can be constrained so that the low energy states embodies an AND operation. So Z is 1 if and only if X and Y are 1. Otherwise, Z likes to be 0 in the low energy state, or an OR operation or an AND operation. And if you map these back into this kind of circuit, you see that you can have, because the way I've drawn this is, by the way, it's not just a Boltzmann machine, it's called what's called a stacked restricted Boltzmann machine, where everything at a particular level or layer here is connected to everything at the layers above and everything at the layers below, but not in the layer, in its own layer. It's restricted because it's connected only above and below, but not its own layer, and it's stacked because it's stacked. So in a stacked restricted Boltzmann machine, you can map these kinds of logical elements onto the elements of this Boltzmann machine, and you can enforce in the low energy states an arbitrary flow-through logic circuit that maps data from the data layer to the classifier level. So I can have, for instance, AND gates and then copy gates and NOT gates going this direction. So, this is a 5 if and only if this and that or that and not this are, equal to 1. And so you can actually enact an arbitrary logic circuit to recognize the data. And that is to say that these Boltzmann machines are computationally universal. Note, however, that they're also symmetric, right? There's no, these interactions are symmetric, so that these weights could also enact an arbitrary flow-through gate that say, if I have a 5, then this fires and this doesn't, this does not fire, and then these two must fire. And so you can have logic flowing in this direction as well. This, I would say, is very important for why deep learning works. If deep learning systems couldn't actually recognize simple logical functions, then they couldn't do any, they would be very bad at learning patterns. Say, for instance, they only had linear relations. Without nonlinearity, then these machines don't work. But because these machines have these nonlinear constraints, like an AND gate, an OR gate, a NAND gate, these are all nonlinear relations between the inputs and the outputs, then you can do computation. So this Boltzmann machine can enforce any computable, in principle, by tuning the weights. You can enforce any computable relationship between classes and data. That is, this Boltzmann machine, it's an Ising model, but it's an Ising model where by tuning the weights, you can enforce any kind of computable function. Okay. And the goal of these devices, this is why it's called a Boltzmann machine, is you want to tune the weights so that the probabilities given by these Boltzmann-Gibbs statistics for these classifier data pairs match the frequency of the data. So if Q of these classifier data pairs is if this is the actual observed frequency, you wish to have these physical probabilities from this Boltzmann distribution matched. So we want to have P match Q. We're constructing a physical system whose Boltzmann distribution matches the probabilities of the data. This is why it's called a Boltzmann machine, in case you were wondering. And effectively, you adjust these weights to try to minimize the relative entropy between the actual data and your predicted data. And for physicsy kinds of people, you know that the relative entropy between your actual state and the thermal state is the free energy of the system. So you're trying to minimize the free energy. See, Hopfield, he makes it easy for us physicists because being a physicist himself, he mapped all these machine learning things onto physics kinds of problems. And then you learn how do you learn these weights? Well, you can learn these states by stochastic gradient descent on the weight space. You check out different weights. You see how you're doing. You have an objective function. Your objective function is just this relative entropy or the free energy. And you try to go downhill in this weight space. And there's a lot of, more or less fancy but sensible things to do, like back propagation. First, you propagate information from the data up to the classifier level, then you propagate it back, adjusting the weights in each way. You do Gibbs sampling. So Gibbs sampling just simply means you sample from your projected distribution, and you try to maximize the log of the probability of your data. This is what's called contrastive divergence, a very sensible idea that works well. Here, and since we've been talking about brains, I've got to be careful because I want to be able to finish this talk on time. But I will talk about this very briefly. There's a very lovely method for training neural nets called the wake-sleep-dream cycle. It's based on what human beings do, or other animals. So what happens is, here's a picture of the brain. Here's the neocortex. Here's the hippocampus. I hope you like my picture of the brain. While you're awake, all these inputs from sight and sound and smell and taste and hearing come in through your sensory apparatus, get encoded through the cortex, and then it sets up this feedback loops between the neural circuits of the cortex, the neocortex, and the hippocampus. And then while you're asleep, the external stimuli go away, but interestingly, these feedback loops are going on and on and on and on. So your brain is very busy while you're asleep with these feedback loops between the cortex and the hippocampus. Interestingly, what's going on then is that while this is happening, while you're awake, you're establishing millions and millions of new synapses, or billions and billions of new synapses in your brain. And while you're sleeping, you're actually destroying those synapses. So it seems that these feedback loops are creating a refined but more compressed picture of what happened to you during the day. And while you're dreaming actually is, the kind of semi-conscious inputs that you get from this process. And it's very interesting what happens. I learned a lot about sleeping and dreaming. So while you're in deep sleep, very deep sleep, you don't really remember your dreams. And these kinds of feedback loops look very similar in functional MRI data to what's happening during the day. When you go to rapid eye movement sleep, however, which is a lighter form of sleep, and the kind where you remember most of your dreams, then what happens is the neurotransmitter called cortisol goes up to much higher levels in the hippocampus, and it disrupts these patterns, and all these feedback loops get mixed up with each other. And as a result, you have all the memories and things that you established during the day, and your thoughts, like all kinds of weird stuff happens. I mean, everybody has had this experience. You have a dream, and you open a door, you're in a room, and you open a door, and you walk in from my apartment in Cambridge into my new house in Oxford, because I have part of my brain that remembers my house in Cambridge, and the part of it that remembers my new house in Oxford, and they get all mixed up with each other. Everybody's had this kind of experience, and it seems completely natural, even though it's completely bizarre. Anyway, this works very well with computers as well. Why does machine learning work? Nobody really knows. Why does deep learning work? Nobody really knows, and there's a bunch of things. So maybe it's that, that you can learn different pieces of the problem. It can be divided into logical subtasks. And doing better on one subtask does better for the whole problem. And so doing better at coordinating subtasks actually allows you to do better in general. Or there's a very interesting set of recent work from the classical literature that suggests if you have these highly redundant, overfitted neural networks, that in this landscape of trying to do gradient descent, there are many possible optima. But local optima, normally you think in this kind of complex landscape, local optima could be really bad, and you do a very crappy job of figuring things out. But it turns out that in many situations, the local optima are all basically as good as the global optimum, which is an amazing thing. At any rate, so what happens if the gradients are small, you have lots of data, lots of layers, lots of times, works pretty well, as Siri and Alexa have told me. All right. So deep quantum learning. Let's see what we could do with deep quantum learning. So we again use this Ising Boltzmann machine-like picture, but the first thing we can do is we can replace the stochastic gradient descent with something like Grover search, and Nathan Weeb at Microsoft has suggested this, or quantum annealing. And we heard a bunch of talks yesterday about taking these Boltzmann machines, these Ising-like models, tuning Ising models, and using quantum mechanical methods to try to find the low energy states. This is just what the D-wave apparatus does. And in fact, these deep neural networks, the D-wave apparatus is a programmable Ising model. And you program it to so that its ground state has physical interactions that enact the constraints of the logical problem you want to solve. And you try to find things that way. So here the deep network is still classical, but the weight discovery process is quantum. I won't say much more about it because we already heard a lot about that. But I think that more interesting, perhaps more interesting, for our purposes to look at universal deep quantum learning. Again, why should we talk about universal deep quantum learning? Well, it's because deep quantum learning sounds cool, and universal deep quantum learning sounds even cooler, right? Universal deep quantum learning, but what do I mean by universal deep quantum learning? Okay, it's deep, so we multiple layers in the network, but we ask in the same way that our classical Boltzmann-like description was capable of universal classical computation, now we demand that our network should be capable of universal quantum computation. And we're going to try to adjust the weights and learn the quantum circuit quantum mechanically, so everything's going to be quantum mechanical here. And to do this, you actually only have to alter this Hamiltonian a little bit. You add tunable in addition to our we add tunable Heisenberg models, like hopping terms to our Hamiltonian. These are terms for you non-quantum mechanical people. These are terms that just take, if I have a 1 here, it allows the 1 to propagate over here and vice versa. So information can now hop in a quantum mechanical fashion through the system. And now you can show that such networks are universal for quantum computation. That is, you can set the Hamiltonian of the system so that it's universal both dynamically, that is, the Hamiltonian will enforce quantum logic to now be performed in the system as information flows from the visible layer to the hidden layer, and also in this ground state, you can enforce the quantum computation in the ground state of your system. Here's how it looks. Actually, this is kind of fun. Here's the nodes to these in this deep quantum learning network. And the idea is that maybe I shouldn't be talking about this, but this is kind of fun. So you start down here, and this line right here tells you that these systems are, you basically have a bunch of particles. These particles are sitting all together next to each other here, and the particles carry with them quantum bits, and they can propagate upward through this network, but they always remain next to each other even though they're not at the same level. And so this surface of states represents, if you like, the way that what a computer thinks of as the states of the logical quantum bits at this point, or now. This is kind of a notion of now. This actually turns out to be equivalent to the Wheeler-DeWitt equation of quantum gravity. And rather than explaining, I shouldn't have put this up, but it actually, there's a direct connection between ground state quantum computing that we heard about a bit yesterday and the Wheeler-DeWitt equation, so, which tells you how the state of the universe, we can talk about that offline. So universal quantum Boltzmann machine. Now let's actually, what we're trying to do, we're giving classical data, and we want to train the weights of our quantum Hamiltonian. So now that the low energy states of our quantum machine now approximate the statistics of our classical data, and as we wanted to generate and classify the patterns in the data, but now we're using a universal quantum computation to generate and classify the patterns in the data. So let's ask some questions. I mean, so we actually, you know, in the very first part of the talk, I talked to you about how if we had a quantum random access memory, we could actually do on a quantum computer, we could analyze data and find patterns exponentially faster than we could classically. So, I mean, in that sense, the answer to the question, can quantum computers find patterns in data that a classical computer can't? The answer to that question is yes, if we can encode classical data in quantum states. Here, we're actually asking, can a deep quantum learner learn interesting things? So for instance, could we learn a quantum Fourier transform? So given some training set, which are, you know, a quantum state and the quantum Fourier transform of that state, can we adjust the weights in this deep quantum learning, universal deep quantum learning network? Can we adjust this to approximate a quantum Fourier transform? I don't know. Quantum Fourier transform is a pretty simple circuit, but it might be hard to do this. Here's another example. We heard a bunch of examples about this yesterday in boson sampling. Boson sampling, we actually have a tunable linear optical array. It's not universal for quantum computing. It's universal for linear optical transformations. And we're assured by work by Scott Aronson and others that if we put in single photons into this array, we propagate them through, then the statistics of the output photons couldn't be generated by any kind of classical procedure with random number generators. This is what's called by the name quantum supremacy, which is a truly hateful name, hate. So I hate this name. Of course, it's rather useful now because, you know, the European Union has this flagship program to spend $1 billion on quantum computing, and Great Britain is investing 500 million pounds, and China is said they're going to invest, you know, 12 billion euros in quantum information technology. So at least I can go to my own government and say, we must restore America's quantum supremacy. And I think our current government might be, you know, more, you know, inclined to do that. We restore and maintain our quantum supremacy. This is going to be expensive, but it will be worth it, right? But actually, the question I'd like to raise is a rather nicer question. So, you know, these circuits, remember, they work in both directions. So they work in, this is actually, if you like, classifier labels down to data. So we have information flowing in this direction, but of course it operates in the other direction as well. So we can ask, if we put data in this part of the circuit and have it flow through back in the other direction, can we find patterns in these classical statistics that we couldn't find otherwise? That is to say, could we use boson sampling to actually find patterns in classical data? I call this supreme quantum learning, which sounds so much better than quantum supremacy. I mean, quantum supremacy sounds like a particularly, you know, a kind of violent and horrible hate group, whereas supreme quantum learning sounds like a particularly delicious dessert, you know, a particularly fine quantum budino, you know. And by the way, these systems are eminently buildable. People build these all the time. I've been collaborating with my colleague Dirk England at MIT. You know, people can build on chip these quantum arrays of quantum interferometers with hundreds of Mach-centered or tunable Mach-centered interferometers. These are experiments we can do. Fabio Sciorino also is one of the world experts on this. So, yeah, can we actually use quantum supremacy? Can we turn it on its head to do supreme quantum learning? I don't know, but we're trying. So another question is, we could ask, well, could a universal deep quantum learner learn how to factor large numbers? You give, you know, input data sets which are the product of large prime numbers and these prime numbers, and then, you know, the classifier, this is our data, the classifiers are P and Q. Can you learn to factor? Well, this seems actually implausible. I somehow doubt that. I mean, Shor's algorithm for factoring large numbers on a quantum computer is a very specific kind of thing, and I rather doubt that you could train something to do this. And the example of quantum supremacy makes the final question that I'm going to end with, because I'm out of time. Quantum supremacy, these small quantum devices exhibit, they spit out classical data that could not have been produced by any classical computer, at least under certain plausible computational complexity assumptions. But the problem with this is, if you look at quantum supremacy, you look at these patterns look almost completely random. So all the examples that we know of that exhibit this kind of quantum supremacy give you data that looks almost completely random. Though we heard a nice talk yesterday, again from Microsoft, or well, primarily from Fabio's group at University of Roma La Sapienza, about applying classical cluster finding techniques, k-means, to find patterns in this data. But the real question is, can deep quantum learning reveal useful patterns in classical data that classical computers can't? I mean, can it find pictures of kittens on the internet? Well, I don't know how useful that is. But for instance, could quantum computers find patterns of what's going on with the brain, and maybe even what's going on in the brain, you know, this is the topology of your brain, this is the topology of your brain on drugs. right? But could it find patterns in things like neural data or financial data or social data that we couldn't find on a classical computer? Now we know that we can, in principle, by things like principal component analysis and finding eigenvectors and eigenvalues and topological methods, that we could do this. But for deep quantum learning, we don't know that. So can deep quantum learning find useful patterns in classical data that classical computers can't? We don't know the answer to this, but I think that just as in the case of classical deep learning, where for many decades it wasn't clear whether it really worked or not, now that we are on the verge of being able to build deep quantum networks that can actually try to do deep quantum learning, we'll find out. So with that, I'd like to thank you very much.
Are there questions? Yeah, please. I think you talked about machine learning, and I think many people first see this classification of data, but at the end you were talking about learning algorithms, quantum Fourier transformation, or factorization.
Yeah.
I think that's even in the classical case.
That's very difficult classically, yeah.
It's meta matching, but not learning algorithms or metas. It's a much more difficult question.
Right, though, of course, as I'm sure you know, I detect someone who knows a lot about machine learning here, much more than I do. So, so as you know, people are trying to use machine learning techniques in things like software development. But of course, for instance, if I wish to learn a circuit, right, if I'm given the output of even a rather small classical circuit, I'm given input-output relations of some Boolean function, and I wish to learn that circuit, that's of course an NP-complete problem, and we know in general you can't do it.
That's where perhaps quantum has another chance, because you have this exponential blow-up stuff when you go from patterns to algorithms, and maybe that's exactly where quantum has a particular contribution to.
Right. Oh, that's a very good point. Thank you for bringing this up, because I should make a warning. I should have said this before. So quantum computers are really good at linear algebra-like things, like fast Fourier transforms, inverting matrices. But the consensus is amongst the community that they probably can't solve NP-complete problems. In polynomial time. I mean, it seems most people don't believe that this is the case. And I mean, it makes sense, right, that NP-complete problems are such a general class of problems that includes, in fact, because it includes basically all possible Boolean functions, identifying them. It can identify any pattern that you could compute. Whereas quantum computers are very good at these things that involve linear algebra, but that's not any kind of pattern. So I wonder, it's conceivable that quantum computers could be better at identifying certain classes of circuits than classical computers. But I don't think that we should expect them to solve NP-complete problems anytime soon. In fact, probably never. But that's a very good point. Thank you for bringing it up.